Recently on this channel, I defended loop quantum gravity from what I think were unjustified attacks on it by Brian Keating. But I thought today we should balance things out by defending string theory from a video that has more than 1 million views. It's by the physicist and YouTuber Angela Collier, entitled String Theory Lied to Us, and Now Science Communication is Hard. And I'm joined to review this by Nick Warner, who is Professor of Physics and Astronomy and Mathematics at the University of Southern California, and was also one of Stephen Hawking's PhD students. So welcome, Nick. Happy New Year. How are you doing?
Doing great, thank you. Happy New Year to everyone. And thanks for doing this. I think it's an important thing to do.
We're going to play a selection of clips from Angela's video, which I think, it has a lot of problems. But if you want to see a more nuanced discussion of the pros and cons of string theory, I hosted a debate between Nobel Prize winner and string theory advocate David Gross and the loop theorist and eloquent science writer Carlo Rovelli. So there'll be a link for that in the descriptions. Do check that out. But for the moment, let's dive into Angela's video and we'll see what she has to say.
This is a video about string theory and how it dominated science and physics media for like 30 years. And as a direct result of that, science communication is really hard now because they lied to us. They lied to us for 30 years, and now we have to pick up the pieces. And I talk about the public response and the duty we have as professional researchers to communicate science accurately.
So just a quick few thoughts. I mean, presumably we agree that science communicators do have to do things accurately. So we're all on board with that.
Absolutely, yeah. I mean, you can take shortcuts, but you basically shouldn't misrepresent the facts of the situation.
Right. But what's interesting is I'm not sure that she's communicating science accurately.
Yeah, in fact, I have a lot of sympathy for some of the points she makes, but in making those points in the way she does, inaccurately, she's becoming more part of the problem than part of the solution to this issue.
Right. And I did a little bit of homework on some of the specific claims because some of them are quite general, but there's one or two like very specific claims. And what we'll see is that I think the data, it doesn't support the claims. So let's have a look at a specific claim that she levels against Brian Greene.
So the Einstein year happened in 1905. 2005, they did like a big 100th anniversary. This is Einstein's book that he republished a bunch of times, but this is like the last like 1940 something version. And because they're republishing it for the big Einstein year, they ask a big famous physicist, Brian Greene, to write the introduction. And I'll just read to you what he says. And remember, this is the year 2005, so he probably wrote this in 2004. But he talks about relativity and how it's a huge deal and how it was such a big thing with physics, and it was a revolution in physics. Oh my goodness, all the things that came from it. And Brian Greene says, again in 2005, he says, now this change from point particles to strings that are so small that they look like points might not sound like it would accomplish much, but it does. Superstring theory successfully merges general relativity and quantum mechanics. Now, does it? Does it, Brian Greene? Have you successfully? Because I actually think I would have heard about a giant test where you successfully merged quantum mechanics and general relativity, but you haven't, and you didn't. You lied. There's the George Costanza thing where it's like, oh, it's not a lie if you believe it, right? But did Brian Greene actually believe 20 years, 30 years into an untestable theory that string theory was going to come out on top? Did he think he wrote that like it was a fact?
Okay, so I thought it would be fun to show a little bit more of this introduction that Brian Greene wrote. So he said, were Einstein alive, I think there is much within superstring theory that he would find compelling and exciting. Superstring theory carries forward his quest for unification. It follows his philosophy, evidence and general relativity, of relying heavily on geometrical ideas to describe the cosmos. And superstring theory shows how general relativity can be made compatible with quantum mechanics. Even so, Einstein would no doubt also view superstring theory with much skepticism. Shortly after they were proposed, special and general relativity could be subjected to rigorous testing. And so when these theories made outrageous claims, they had to be taken seriously because experiments had shown that the theories work. To the contrary, superstring theory does not yet have experimental support. Making two experimentally confirmed theories, general relativity and quantum mechanics, compatible is an important step, but no one will be convinced that superstring theory is right, that it is the unified theory that Einstein sought, but never found, until the theory is itself confirmed experimentally. With the increased power of the world's accelerators and even more refined telescopes gathering data of unprecedented precision, such confirmation could happen within this century. Now that's important actually, because what we'll see later on is that she keeps saying, it's all going to happen within a decade. But here he's clearly saying it hasn't been experimentally confirmed. It needs to be experimentally confirmed. And it might, not will, but might happen within this century. This century, of course, he wrote it, as she said, probably in 2004. So, we've got 75 years left. And it carries on saying, if so, Einstein's theory of relativity would be seen as part of a much grander theoretical synthesis. If not, the world's physicists will no doubt carry on the search for unification down other avenues. Some other approaches, such as loop quantum gravity, are already highly developed and being pursued vigorously. So it seems to me that Brian Greene didn't say what she said, or at least that she's taken the quote out of context.
Yeah, there's a huge can of worms that you've opened up here. First of all, there's the issue of unification, and then there's the issue of making a quantum theory of gravity. So just let me background a little bit. We have two amazingly successful theories. We've got quantum mechanics, which describes the output of light bulbs and describes how computers operate. Fantastic theory, precision tested to unbelievable levels. Then we have general relativity theory, whose biggest precision test probably was the merger of black holes seen in LIGO. So we got these two cornerstone theories of modern physics, but they kind of hate each other. They have fundamentally different descriptions of matter, which is extremely massive at very small scales. So there's always been this tension ever since the 50s that making a quantum theory of gravity is hard. And people have tried and tried and tried over, 50, 60, 70 years, and largely failed until string theory came along. So basically, we came up with ideas. We tried to make quantized gravity itself. We tried to create supergravity, and all of them failed at some level when we tried to make the quantum theory work. The thing about string theory is that it contains general relativity theory. It is a quantum theory of nature, and it seems to work. Now, I'm being very careful. Seems to work. Every single test that we have thrown at it, that other theories failed on, string theory basically passes. So string theory has yet to fall on its face.
Let me interrupt. When you say test, I presume you mean a theoretical test. It passes some. You don't mean experimental test, right?
No, I don't. So thank you. That's part of the can of worms I need to sort of sort out. So test in the sense of we do a calculation. Does the answer make sense? We don't even compare it to experiment. And so some of the answers in supergravity just don't make sense. So when I say test, it's a theoretical calculation. Can you first do the calculation? Second, is the answer ridiculous, or is it actually consistent and making a sensible answer? And string theory has passed basically all those tests in theoretical tests. So while we haven't a definitive proof that string theory is a good quantum theory of gravity, it has really satisfied an awful lot of theoretical exploration and tests that have failed. So there's never been a party, yay, we've got a quantum theory of gravity, hey, let's all celebrate, because we never got the final theoretical proof. We've come very, very close. And so I think the predominant sentiment in string theory is indeed string theory is in fact probably the only viable theory of quantum gravity. So Brian Greene in that Einstein book was not lying. He was representing the belief based on a huge amount of theoretical exploration that string theory is a quantum theory of gravity. There isn't a mathematically rigorous proof, but it's getting close to the reasonable doubt criterion. And so therefore we tend to assume that we could fall on our face. Somebody come along and say, hey, here's a calculation of string theory that just shows that your theory is rubbish. Could happen. Hasn't happened yet. Now, then there's the issue exactly of the test against observation. And Brian what he says is absolutely sober and correct about that. String theory has had so far no observational tests. So when Angela talks about, well, I think I would have heard about a great test, she's using the word test to mean, oh, this is a thing that you can do in an experiment. The problem with quantum gravity is it's a much deeper level. It is unlike any other thing we've had in the past in physics. Normally physics, we have a bunch of theories, all of which work and make sense, and we test them against observation. Here, we're struggling to get one theory that works, and the only one that we have really is string theory, superstring theory. Quantum gravity, I'm not going to touch, but I don't.
We're not going to go there. But if you want to go, if people want to go there, they can watch the debate that Carlo Rovelli.
Yeah, exactly.
And you can judge for yourself. We're not going to go there.
You can bet which corner of that debate I'm in.
Yeah. But what I want to do is actually a bit more defense of Brian Greene, because I've dug up some old videos of what he said, one in 1999, when his first book, The Elegant Universe, came out. And then later on, when the Nova documentary came out, which was also called The Elegant Universe, it was an adaptation of the book. But at the same, I think roughly the same time, he had his follow-up book. I think it was called The Fabric of the Cosmos. So that was a couple of years later. And I've got a couple of clips of what he was saying. And I think it was not saying, we're done, it's all confirmed, or neither was he saying we'll be done in a decade. He was saying this is a promising avenue, an exciting idea. We're all super excited about what's happened, but it is not done yet. And he does specifically say we need experimental confirmation, which we don't have. So I don't think he was misleading the public, but let's have a look at the clip and we'll see. You can judge for yourself.
How far off are we?
That's a tough question. We've made a tremendous amount of progress in the last 15 years, more than anybody in their wildest dreams would have imagined possible. But there's a way to go. And what we now know is that superstring theory, we believe, is paving the way. It's really showing us a direction towards that final explanation of everything. But it could be 5, it could be 10, it could be 100 years before we know whether this theory truly is the theory of everything.
All right, you said a decade. It's been a decade.
Have we in the past thought we had it, thought we were close, and it turned out to be much more complex than we imagined?
Yeah, absolutely. In the turn of the previous century, there were some physicists who thought that physics was basically over and a few details were all that remained. And that was before relativity, that was before quantum mechanics, that was before any of the real deep puzzles and structures in the universe were really laid bare. So it's right. It's possible that we are fooling ourselves, but this is the first theory in the history of physics which doesn't need anything else for it to make sense. This is a theory that could describe everything, and that's something that all previous attempts at having a final theory could not claim. So I think many have come to the conclusion that although we don't know whether it's right or wrong, and we won't until we have experimental evidence, that really is the arbiter, but has had such progress and made such strides that it needs to be taken very seriously.
So it seems to me that he did make the caveats that were needed. Like, it hasn't been experimentally tested. It needs to be experimentally tested. He just didn't say, that this is like a done deal, that it'll all be done in a decade. He said quite the opposite, in fact.
No, absolutely. And it's all about the thing about string theory, also, and Angela says about experimental tests of string theory and experimental predictions. It does make predictions, but Brian alludes to the fact that it's going to require accelerators of extremely high energy or something that involves probing very subtle details. And what Brian is alluding to at the beginning of this is at the turn of the 20th century, 1912 or so, Rutherford determined the structure of an atom. And they thought, okay, it's all done. We figured it out. But then those details to do with atomic spectra led to quantum mechanics. So those little details that you haven't quite got right often are a clue that there's something much deeper buried underneath. And many of us suspect this is true with string theory. In particular, there's this paradox we talked about called the black hole information paradox. There are details about how quantum mechanics interacts with the horizon of a black hole that lead to details that just don't work out. And so many of us believe that this is a signature that we need a better theory of gravity, and string theory is by far and away the best candidate for that as far as I'm concerned. So the details might emerge from black hole physics. They might have emerged from the cosmology of the very early universe, but if I'm a betting man, I'm going to bet on black holes.
Right. So the claim, let me challenge you a bit, because you said that string theory does make experimental predictions.
Yeah.
Like what? Give me one.
So it predicts there's a huge spectrum of particles, new particles that we haven't seen yet. The trouble is the masses of these particles are so high, they're well beyond the range of current particle accelerators. 10 orders of magnitude or so, or 12 orders of magnitude. They're hugely energetic. But we don't see them, and there's a reason why we don't see them. We don't have the energy to make them freely available in our laboratory, in our houses, but also in the biggest and best particle accelerators. So you don't see them directly. But when you have a superabundance of energy, like when something falls into a black hole or in the Big Bang, you should see them. That's why there might be signatures of string theory imprinted in the Big Bang or in infall. So yeah, there are lots of predictions, but
hang on, let me interrupt, Nick. So I want to be clear. What you're saying is that, because some people say in principle, string theory cannot be tested. In principle. And what you're saying is, at least in principle, by doing black hole physics, by doing early universe cosmology, it's possible that a signature of string theory could be seen.
Let me back it out. Look, a theory, I present you with a theory. The real brilliance of an experimentalist is to find the way to tease out the information. I'll give you an example. Ground unified theories. The energy scale there is 10 to the 15 GeV, which is about 10 or 11 orders of magnitude higher than the most powerful particle accelerator on Earth. One of the predictions that comes out of ground unified theories is the proton is unstable. And it decays on a scale of 10 to the 30 years. So you have to wait 10 to the 30 years to see it. That's a subtle detail. But the brilliance of the experimentalists here was say, but I don't have to wait 10 to the 30 years. If I put 10 to the 35 or 10 to the 31 protons in a box and turn out all the lights and watch for the ping of one proton decay, I can check this theory in a year. And that's exactly what they did. And the theory was found to be wrong. So the point being that if there is going to be some clever thing that you can do that may be at more modest energies, you can see a signature of string theory. I don't know what that is. But I do know that there are things in the universe that can access the incredibly high levels of energy that are needed to see what are called direct stringy effects. The fact that there are extra particles, the string becomes excited and therefore generates all these new particles. One of the processes where this obviously must happen is in the very early stages of the universe in the Big Bang. And the other way, which is actually, I think, going to become important with our precision observations of black holes, is when something falls into a black hole. A black hole is a fantastically powerful natural particle accelerator. The particles fall in, approaching the speed of light before they hit the horizon. And if there is any structure in the quantum gravity aspects of the horizon, you're going to see it or at least it's going to change the way infall happens into a black hole. Whether we can see it will require the observers at LIGO and LISA to tease out these incredibly subtle details. But it's possible. So black holes might give us a window into exactly the energies we need. I'm optimistic. That's the failing. In fact, I think Angela's getting. We're optimistic about things that might be possible, but we just have to refocus the optimism every time we find that something doesn't work and we have to find a new way for looking at it. But I think the focus on the early universe and the focus on black hole physics is the best place to look for string theory at the moment.
Let's move on to the next clip from Angela's film.
But I have had conversations with the public, because I do observing nights and stuff, where someone comes in and they're like, they don't actually know the density of Jupiter. They can't actually measure that. They're just saying stuff. And it's just we can measure the density of Jupiter right now. Me and this person who said that, we take a single image, we look up Kepler's laws, and we can measure the density of Jupiter and be really, really close. And that's beautiful and wonderful that physics has mathematical structure. We can make an observation and we can get an answer. That's what physics is. That is not what string theory is. And they lied for 30 years, and now all the people think string theory is physics, and we have to earn their trust back. And that sucks, man.
So I thought I'd check some of the claims here, because I think the overall narrative is that, string theory lied and then people don't trust science anymore. So I wanted to see, is there actual data to confirm this? Obviously, the data is limited. I was disappointed that she didn't refer to any data, any studies whatsoever to back up her claims. And I thought, surely she would think that data to support claims is kind of important. Even when you're doing social science, there's no excuse for not looking at whatever data you can. So I had a look at the data, and what I found in this study, which was from Pew Research, was that confidence in science seems to be roughly steady. It's stable since the 1970s, says the study. And what you also see is there has been a decline, but only in medicine. So if you took out medicine, it would look like quite, maybe a bit more significant uptick. So it doesn't look like there was a big decline in the trust of science at all. The data just doesn't seem to support that. Now, this is in the United States, but she does say, she's looking at the United States as well. So that doesn't seem to support it. Now, she also says later on, we'll see, that it's in the 2010s that the public sort of realize they've been scammed by string theorists. And so this should be where we see the big downturn. If you look at this graph, if you look at the 2010s, if anything, there's an uptick. There isn't a downtick at all. I mean, it's just not there. There's another study I looked at here. So in this study, people were asked various questions. I think the one that will become important later is whether the federal government should fund scientific research. So again, the claim is that in 2010s, the public realized they were scammed. Now they distrust scientists and they don't want to fund science or maybe particle physics. But what you see, actually, if we go to the beginning of the survey period, which is in the early 90s, the level of support for federal government scientific research is in the late 70s. So what we would expect is a big downturn in the sort of 2010s going to today. And we don't see that at all. If anything, it's slightly higher. It looks like it's in the early 80s. I sort of guess about 82, 83%, something like that. So we just don't see at all what she claims we should see. Okay, so that data doesn't seem to support her claims. Now, there is one bit of data that does seem to show a decline in public trust of science, and that's this next survey by Pew. Now, unfortunately, the survey period doesn't really cover the time that she's particularly interested in, which is the 2010s. So what we'd love to see is before the 2010s and then after the 2010s. And unfortunately, we don't have that data. But what we do see is that public trust of science is, now they've split it up between Democrats and Republicans. And what we see is a very big decline in Republicans. So between Democrats, the start of the survey period, it's gone from 72 to 69. There is a bit of an uptick in the middle, but from 72 to 69, I don't think great big decline. But the big decline is obviously in the Republican trust of science. I very much doubt, I don't know, it seems hard for me to believe that's anything to do with string theory. It looks like the turning point is the pandemic.
Right.
And what do you think, Nick?
I think this is true. I mean, certainly this looks exactly like the pandemic, the correlation with the Republicans. I mean, the trend, particularly in medicine, the fact that we now have Robert F. Kennedy slated to become the head of healthcare in the US. This is a trend that you see strongly in the Republican Party. You see it in the Democrats too, because the pandemic made all our lives miserable. And if you make people's lives miserable, you're going to try and, it's going to reflect in your trust in the people who are trying to address the issue. So medicine for sure. I don't think there's been a huge change in physics. I think the public trust in science has remained constant. The danger, I think, is the danger that we face directly in every aspect of our life. It's the predominance of people getting their information entirely from their social media bubble. And I think that can happen in science. You see it with, influencers who perhaps want to peddle vitamins or particular exercise techniques that then create this bubble. And in science, you can get the same thing. Actually, to Angela's credit, she's got a very engaging video about crackpots. And I looked at this, I thought, this is great. I mean, she's really caught. But the thing with crackpots is they sit in their own bubble with their own sort of self-referential information. That is a real danger. But it's a danger in every aspect of our lives, political lives, social lives, whatever, that you get caught in this bubble, which can take you away from, facts and experimentally testable reality.
Right. Okay, so let's move to the next clip.
In the 80s, the physicists are like, this is really neat. I'm excited about this string theory. Remember, they called it the first big revolution in string theory. They're like, we can explain quantum gravity or a type of quantum gravity. And a bunch of physicists start going to work in string theory. They're like, this is exciting. You know, more physicists are working in string theory, and departments across America, I'm sorry, I'm always really American centric, are hiring string theorists. They're like, oh no, this is the next hot thing. Like, we're the University of Illinois. We need to get a string theorist in here. And they're like this big hiring boom in string theorists, and people are talking about string theory, and they're like, in a decade, they said, it's gonna happen. In a decade, we're gonna get there. It's gonna be amazing. In 1995, Ed Witten, I've mentioned him, he comes to a conference with a paper, and he's like, guys, we have all these theories of string theory. They're all multi-dimensions. They're all different dimensions. But listen, I have done the math. This is Ed Witten talking. He says, I've done the math, and it turns out you can move between these theories. They're actually all the same theory. If you watched my mass video, I talked about the Lorentz transformations between reference frames. Like, you can just do a conversion and go from one reference frame to another, and you can do the same physics. That's a similar thing here. Ed Witten is like, all of these string theories are the same string theory. This is amazing. And the public, no. The public, the audience at this conference is like, this is amazing. This is a validation of string theory, because, like I said, people, they want physics theories to be beautiful. And the idea that you need 10 different string theories is not beautiful, but the idea that they're actually all the same string theory is very beautiful and very exciting. So the string theorists see this as like a confirmation of their theory. It's not. It's a very interesting mathematical tool and idea, but it's not a confirmation of string theory, but it's fine. They're like, this shows you, they think this shows you that we are working towards something real, because all of these theories are the same theory. And this is called the second revolution in string theory. And like, I mean, they're playing really fast and loose with the term revolution. If you haven't had a single experimental verification, can you have multiple revolutions in the same theory? I don't understand. But this is the second revolution in string theory. And they're like, you guys, in a decade, big things are going to happen.
She's given a little history of string theory. Is it accurate?
The meeting she's referencing is a meeting in 1995 that was held at University of Southern California, a meeting that I helped organize. In fact, Ed Witten gave the talk on a Tuesday morning when I was actually chairing the session. I was there, and that's not exactly what Ed Witten said. There was a realization growing in the string theory community, starting earlier, that all these different string theories might actually be different manifestations of the same underlying theory. It's probably one of the most significant steps is a paper by Hull and Townsend that was about a year before. And I think Ed Witten drew heavily on that particular theory in his talk. So he gave a talk which galvanized and really was an exciting talk, but it was pulling together really important threads that led us to understand that all the apparently different string theories are really different phases of some underlying structure. The first string revolution was really in 1984 when we realized that, string theory might actually produce a viable theory of quantum gravity. There were these experiments, theoretical tests that we had done. Every other theory had failed, or most other theories had failed. String theory passed it. And Greene and Schwartz and Witten really propelled the first revolution. The second revolution was we got all these string theories, but really they're just different aspects of the same underlying structure. So the word revolution here is being used in the sort of sense of paradigms, the sense of a deeper understanding of this theory. We still don't have the revolution that says, and it is describing nature faithfully according to this experiment. But this is one hell of a change in the way we thought about stuff. So it is a revolution. In the same way that when you change the way you think about anything at a fundamental level, it's a revolution.
I'm just wondering if there's an ambiguity about the word confirmation, because surely can that be used in different meanings? Like, so for example, if I have a theory and I experimentally test it, that's a confirmation of the theory. But also, could we not say anything that gives us more confidence is confirmatory?
Yes.
Maybe in a basic sense.
And so to some extent, that's what as string theorists, we hang our hat on. So because we don't have a direct confirmation of an experiment, we can now look at string theory and say, what does it tell us about things we already know about? And one of the things string theory has done is produced a lot of spin-off technologies where it has given us a much deeper understanding of things that we have tested, field theory and things like this. There's a huge enterprise that's involved in calculating complicated processes in particle accelerators that just came straight out of string theory. It was a technique that spun off. Similarly, in the mid-90s, Seiberg and Witten gave us a much deeper understanding of supersymmetric quantum field theories, which we think has more direct connection to experiment. But this ideas came out of string theory. So in a sense, the confirmatory aspect of this is if you take string theory and try and reduce it to something you know, and does it clash or does it give you a better and deeper insight? And generally speaking, it's given us amazingly better and deeper insights into things that we know are part of nature.
Let's move on to the next clip.
The other physicists are like, all right, you said a decade. It's been a decade. What's going on? What's going on? And this is when the physicists, the experimental physicists, realized that string theory is not testable, right? Like, you have all these dimensions. Like, we can't actually observe all these dimensions. Like, how could we ever test this theory? In fact, is it a theory? Is it a theory if you can't test it? Is it a theory at all if it is experimentally unverifiable?
So a theory means different things to different people. When you hear evolution contested, you say, well, it's only a theory. People have theories about fairies at the bottom of the garden, or about God, or theories about social structure. In science, when we talk about a theory has to make a prediction, and that prediction must be able to falsify the theory. That's what makes science science. The falsifiability of a theory through experiment or observation. That's the critical thing. So Angela, I think, is kind of tying herself in knots about what is a theory throughout this piece, because she's conflating all the possible meanings of the word theory. So let me be absolutely clear about string theory. It is a theory, and it is a scientific theory. It makes predictions. Now, there's the in practice, and then there's in theory. In practice, it's extremely hard to test those predictions at the moment. At the moment, we don't have a way to do it. We may have some brilliant experimentalist who comes up with a way to test this thing. But string theory certainly makes predictions. It predicts particle spectra, all sorts of exotic particles. It predicts what happens, but only at energy scales that are so high that we cannot access them with particle accelerators. But as I said before, there might be workarounds in some of the subtle details of observations. So, string theory.
Let me challenge you here.
Yeah, sure.
How in principle, like imagine, the most amazing piece of technology you can imagine. In principle, how would you what observation could we make that would say string theory is wrong?
Okay, so if I made a particle accelerator that operated at 10 to the 19 GeV, which is 15 orders of magnitude better than anything we've got, then I'd slam particles together and I should see this cascade of new, amazing and exotic particles. And they should conform to a particular set of behaviors. There should be the so-called Reggie spectrum. There should be all sorts of really cool features that string theory says this will be this part of the spectrum, and this is how they will behave as you crank up the energy and you crank up the angular momentum and things like this. So string theory makes extremely precise predictions about what happens in particle accelerators at 10 to the 19 GeV. The practical problem is we don't have such an accelerator.
I will probably never have an accelerator.
Never have, but black holes might do it. The early universe might do it. But then I say, the cautionary tale I say with that is, it's the subtle detail argument. It's the grand unified theory argument. The grand unified theory on the face of it requires 10 orders of magnitude better than anything we've got. And yet, if you make a very clever, subtle experiment, you can falsify the theory or test it within a year. String theory, we haven't been able to think of such an experiment. It's just hard. And I don't know. I confess defeat. I don't know how to do it. As I say, I know a lot about black holes, so that's where I'm putting my money in terms of trying to figure out how you might see observational signatures of string theory in black hole physics. But It's hard.
And I just want to represent a different opinion, because reading some literature on the philosophy of science, I know most scientists I speak to, they say, yeah, falsification is the way you define scientific theory. If it's not falsifiable, it's not a scientific theory. But, and this is something we mentioned in the book, in the ISF, Shorty and I have written a book on cosmology. It's coming out in May, The Battle of the Big Bang. If you survey philosophers of science, they don't really agree. They think that there isn't a single definition. There isn't a single criteria to define what science is, that it's more complicated than that. And some people would say, that a theory is simply an explanatory framework. So what you need to be a theory, so you take a bit of data and you explain it in one sort of framework, and that's a theory. What you need, the experimental side, is not needed for it to be a theory. It's needed for us to think that the theory is true. So you can be a theory even if you make no predictions at all. But we just wouldn't say the theory is true until we've made the predictions and we've confirmed them by the friend. So there's an alternative view. I know it's not necessarily your view.
But that's, I don't think we disagree. There is a notion of a theory across every subject in the world, but a scientific theory. So that's the adjective scientific is extremely important, is the one that's falsifiable. It describes nature. You do experiments, you test it. So the theory of electromagnetism, theory of evolution, those are things that have been tested up the wazoo, and we know absolutely they're true. String theory has not been tested, but it is an amazing framework to understand nature at a deeper level. And at the moment, that's all it really is. It's not making it, the predictions it makes can't be tested. So it is still in that sort of framework stage. But in principle, but it is a scientific theory in that it makes predictions that can be falsified, just not by us at the moment.
Okay, so let's go to the next clip.
Another thing that happens in the 90s is the development of supersymmetry, which again, I don't want to go into, but all the forces freeze up into one force. You can use one theory to explain all the forces, and it's symmetric and it's beautiful because that's important to us. That one thing the particle physicists do is they look at this idea of supersymmetry and they're like, ooh, what if we had this, but in particle physics? What if we had a supersymmetric extension of the standard model, you know? And should I do it? I'm not going to do it for that. And so particle physicists, without the string theorists, develop a supersymmetric version of the standard model. And because they're particle physicists and the standard model is a very successful theory of physics, they immediately develop an experiment to test this idea that they have, and they start getting funding for it, and they will test it in the next decade. That is, of course, in opposition to the string theorists who have not yet proposed experiment. And I'm sure you can find them proposing experiment, but the issue with the multi-dimensions is that if you don't get your expected results, you do have an answer, which is, oh, we just couldn't observe it this time. Like it wasn't in a dimension we could observe. And like that can't be your working model of physics. That just can't.
So let's talk about supersymmetry. I mean, is it fair to say that string theorists were hoping to find supersymmetry at the LHC? They didn't find it. Isn't that bad news for string theory?
More sociological bad news than actual physics bad news. So let me explain. Supersymmetry and string theory are intimately related, but they have become separated as concepts. Supersymmetry started actually as part of string theory in the early 70s. Angela's chronology is a little bit off. Supergravity came into being in the 1970s, and the supersymmetric standard model was early 1980s. I think the minimal supersymmetric standard model is 1981. So it's way before the dates she's talking about in this piece. Okay, so in superstring theory, they are supersymmetric, but the supersymmetry is only manifest at these insanely high energies, the Planck scale, 10 to the 19 GeV, in the pure form of the theory. And to falsify it, you have to falsify supersymmetry at that energy scale. That's why it's so hard. Now, optimists said, well, perhaps we can use that supersymmetry at a lower energy to solve what's called the hierarchy problem or the naturalness problem. There is the natural scale of the universe is set by the Planck scale, the theory of where theory of quantum gravity is. But the particles we see are, protons, quarks, whatever, have much lower energy. And how could you explain that in a sort of top-down model where you start with this fundamental theory of everything? And so people realize that one way you can protect and stop particles all having insanely high mass is through what is called low-energy supersymmetry. So there's an additional postulate, which is there's a huge amount of supersymmetry at very high energies in string theory, but a little bit of it might survive to low energies and solve another physics problem called the hierarchy problem, and that we can then test in particle size. So this supersymmetric field theory, the minimal supersymmetric standard model, is an expression of this idea that maybe a little bit of supersymmetry survives to very low energies, solves another physics problem, and we might see that supersymmetry. It's not completely dead, but it's really being corralled into this little tiny corner of possible true models. So I wouldn't be completely out on supersymmetry yet, but it's looking pretty bad for low energy supersymmetry. But that's a completely separate hypothesis or theory called low energy supersymmetry, which does not invalidate the high energy supersymmetry that is needed for string theory to work. So, yeah. Sociologically, it would have been really nice if one of the core principles of string theory that we believe in actually turned up in nature at very low energies, but it didn't. But it doesn't invalidate the string theory. So that's why I said it's a sociological hit. It means that a core principle that we hope we might see at low energies, we didn't get to see, at least yet.
Right. So something that Carlo Rovelli said, tell me if you agree with this.
Mm-hmm.
He said, look, had we found supersymmetry at the LHC, it would not have proven string theory, but it would have given us a boost in our confidence in string theory.
I think that's exactly right. I think
and then he says, there's another bit. Uh-oh. Then he said, the fact that we didn't find it doesn't disprove string theory, but it means it takes a hit. So it would have had a boost, or it takes a hit, depending on whether we find it, but neither of it proves or disproves string theory. What do you have to say?
I think it depends how you define hit, but yeah, that's what I meant by the sociological issue. The point is that if you're now, it moves string theory into this rather rarefied situation where you have to find some other test of extremely high energy. And so if you're a practical grant administrator and you go, well, I would like to fund things that are going to be tested in the next few years. I was dumping all this money into particle accelerators to look for low energy supersymmetry, didn't find it. The knock on the hit is simply, okay, maybe the funding priorities will be shifted as a result. That's the hit. That's the sociological phenomenon. But it doesn't mean the theory is wrong, but maybe the theory the theory landscape, and the practice of supersymmetry, or practice of particle physics, string theory, will shift a little bit in response, simply because we didn't get the carrot that we really would like to have got. So yeah, I agree with it.
All right, let's go to the next clip.
When the multiverse idea starts getting very popular, like not only are there multiple dimensions, but there are multi-universes that again we cannot observe. And the string theorists, of course, they write their books and they get their money and they talk about the multiverses because, of course, people are interested in this idea. That's an exciting idea, even if it doesn't have any physics backing or experimental verification even possible. That is something that someone who's just a casual viewer of physics would be interested in learning about. So they write their books and they get their cash.
Let's talk about multiple universes then, because there has been this claim that string theory predicts a landscape of at least 10 to the 500 different solutions, and that these are realized in model like eternal inflation. It could be more than 10 to 500. I've heard some people claim, 10 to the million, 10 to the infinite. And so this is actually, a really big problem for string. I mean, some people like it because maybe it will solve like some claims about fine-tuning of the constant nature. Some people hate it because it means that they think the theory is completely untestable, then even in principle. So what should we think about this multiple universe claim?
Okay, so before we just jump in there, I'll go there. I've meant to respond to Angela's comment about many dimensions. String theory is built in many dimensions, and she remarks at some point, how can we observe them? We can observe them. It just requires extremely high energies. So this spectrum of particles I talked about emerging at 10 to 19 GeV, that is coming from those extra dimensions. So extra dimensions are testable and observable. Now, let's get into the rabbit hole of other multiple multiverses and other universes. Okay, we only live in one universe, and therefore, well, at least as far as I know, and therefore experiments that I can do are basically only within that universe, and I can't talk to the neighboring universe. So once we start talking about multiple universes, I begin to lose any sensible bearings I have. I'm not a fan of the multiverse. I'm not a fan of any of this stuff. And here's my reductionist viewpoint. If another universe interacts with me, then it's part of my universe, and I can interact with it, and I can measure it. If it doesn't interact with me, I will never know it exists, and I don't care, and it's not part of my physics. But how did multiple universes come about? I think we don't want to go down the many worlds interpretation of quantum mechanics. That's an older story and not connected to the new stuff about multiverses. So in the multiverse, the idea is that maybe a universe can bubble off from our universe, or maybe we all bubbled off from some substrate below in internal inflation, and we all live in our own bubble universes. It is a possible solution to the theory. So let me see what I mean by that. When you have a theory like string theory or general relativity theory, it doesn't completely determine the physics. What you have to feed into it is some initial condition or some boundary conditions or something like that that shape how those equations evolve, and then that tells you how makes predictions for you. But you have to put in at the beginning something about what the initial conditions are. And this landscape story with 10 to the 500 or 10 to the 1200, whatever possible solutions, is really a statement about how many solutions there are to those equations of motion that one can make, relatively easily or in principle. This is the trouble with this aspect is it gets into this very undefined thing where you say, well, I live in one solution, I'm going to measure that. That would be my attitude, and I think the attitude of a significant portion of the community. But the equations do allow you to build these exotic and crazy structures. In fact, some of the equations, if you push them to extremes, allow you to perhaps bubble off a baby universe from our universe, and then it goes on and becomes a universe. We can never influence it again. So I would separate off the intellectual enterprise of the multiverse from string theory. You can build models of the multiverse using just gravity and a bit of baby quantum mechanics. So, it's kind of loosey-goosey physics because the calculations aren't that rigorous. They're heuristic calculations. I frankly don't believe them. I'm a conservative. I believe in, doing real math with real calculations where you state your assumptions at the beginning, you come to the conclusions at the end. I find this stuff on the multiverse a bit too loosey-goosey for my taste. But it's an interesting enterprise, and a lot of people do it. But it is not just string theory. There's a lot of people who have never written a string theory paper in their life who write copiously about multiverses. So I would say, hey, I will accept the good and the bad and the blame for string theory. That's my job. But the multiverse, that's something else that is an entirely separate intellectual tradition, and I'm not a great fan.
Right. So just to be clear, you're claiming then that this 10 to the 500 possible different solutions to string theory does not mean that we should expect that there are all these other universes. It's just different solutions to a theory, just like any theory can have different solutions depending on what you put into it.
That would be my attitude, that there are, but then you've got a huge problem. So one of the problems with string theory and cosmology is that you've got these equations which are unique in some sense. There's only one string theory, but they have a lot of solutions. And so the problem of pinning down which universe we live in now becomes, how do we know, or why did it choose this particular one of the 10 to the 500? Or that it's more than that now, but there's a huge number of solutions. Also, the thing that's really hard to do in string theory is to make solutions explicitly with positive cosmological constants. The universe is expanding in an accelerated manner. We have dark energy, it's driving the universe faster. Finding explicit solutions where it has that positive dark energy is actually very hard in string theory. The people have talked about how you might do it. They've come up with scenarios, but getting something where you can really get your hands on it has still been something of a challenge. So,
and I'll just do a little plug for the book that we've got coming out in May, because in this book, The Battle of the Big Bang, we talk to a lot of the proponents of the multiverse, and critics of the multiverse. And interestingly, one of the critics, Robert Brandenberger, works in string cosmology with Kumran Rappa. So it's not. So I think there is an interesting discussion to be had about the multiverse. Is it physics? Is it good physics? What is it? But I don't think it's necessarily always on this all multiverse proponents are string theorists and, critics on the other side. I think it's more nuanced than that. Okay, let's move on to the next clip.
Leonard Susskind in 2008 is like, the LHC is going to confirm supersymmetry. So the Large Hadron Collider, that's one of the experiments that the particle physicists had developed to test their supersymmetric extension of the standard model. Remember, of course, that is not a string theory. That is an idea that was taken from string theory and applied to the standard model. So it is not a string theory. It is a particle physics standard model theory. But Leonard Susskind, string theorist, is like, it's coming up gravy, baby. The LHC is going to test it, and that will be experimental verification of string theory. But that's not true, because, spoiler alert, supersymmetry is dead in the water. But if it wasn't, if supersymmetry had been experimentally verified by the LHC, that would have been an extension of the standard model. It would have been experimental verification of that extension. And it would not have been anything to do with string theory besides that they got the idea from string theorists, right?
Okay, so I just did a little bit of fact checking on this claim about Leonard Susskind. So here is the book, Black Hole.
Oh, no.
The Black Hole War. Okay. And what he actually said about supersymmetry was, at somewhat larger mass, there is a whole collection of particles whose existence is only conjectural. But a lot of physicists, including me, think that they may exist for reasons that are not important to us here. These hypothetical particles are called superpartners. Then in a footnote, he said, we will have within a few years when the European accelerator called the LHC, Large Hadron Collider, starts operating. So one, he did say that they were conjectural. He didn't say they do exist. He did say they just may exist. Now, he was, I think, a little bit sloppy with his language because he said, we will know when the LHC, starts operating. But he didn't say what we will know. It could be that what we will know is whether there's evidence for superparticles or supersymmetry. He didn't say we will find supersymmetry at the LHC. He absolutely didn't say that.
Let's just take this in two pieces. One of which is what Andrea and what Lenny is talking about is this low energy supersymmetry that does not have to be. Falsifying that does not falsify string theory. It would have been a nice plug if it did. So that what they're talking about, these super partners and everything else. So the physics world was split. Basically, the traditionalists sort of thought, okay, if low energy supersymmetry is found, that's great, but it's not essential. But what happened then when you turn on the LHC is that they started looking for this stuff. And there's a sort of theory space of supersymmetric standard models. And you've got some parameters you can tweak. And what happened was that theory space sort of large amounts of it just started getting wiped out. So the numbers of physics papers dying on a monthly basis was probably huge. And what's left is perhaps some tiny little corner of that space. The LHC is not powerful enough to eliminate that corner, but 98% of it was destroyed by LHC. So what it really means is that many of the models that people had out there were just plain wrong. There's still a few that are left that might still be viable, but, time will tell. And so I think Lenny's statements there are accurate. Now, let me add a sort of more personal note about all of us. All of us tend, if you're going to do this for a long time, it's got to excite you. And so string theory excites me regularly. It's really an amazing subject. And that's true for everybody who works in the field. Now, some people let that excitement perhaps, make them express their optimism perhaps too forcefully. I think Lenny is perhaps guilty of that from time to time, that says things. If you know Lenny, he's out there and he's saying things that are just provocative. And so I think he's perhaps being optimistic. So while you're right, the quote isn't there, I could easily believe that Lenny had said something like that off the cuff, because when you're excited about something and you're perhaps not as guarded as you should be, then, You can say things that are perhaps too strong and the number of times I've been at public talks and listened to Brian or listened to something and saying, "Oh, okay, that makes me feel a little uncomfortable." And it's just because they're taking shortcuts or they're expressing optimism that perhaps it goes beyond mine. But we all do this to some degree. And so let's just build back in there that there are human beings doing this and they get excited about what they do. All
right. So let me put the direct allegation then a little bit clearer. The allegation and maybe the quotes that Angela had, I don't think they check out. I honestly think she's just got it wrong. But that doesn't necessarily mean that string theory hasn't been overhyped. And that might mislead people. Right. What do you want to say to that? I mean, do you think it's true that it has been overhyped? And what does that mean for physics?
I think, okay, this is actually a cultural thing as well. There's the US and then there's Europe, and then even within different countries in Europe, there are different attitudes. So in the US, things tend to get hyped more. It's part of the culture. It's the way we are here. And so string theory, yes, definitely was overhyped. There were promises. There were unguarded statements that were made about how it's going to change the way we think about nature. Now, it did, but at a much more subtle level. So yeah, it gets overhyped. But other things, when you have a collection of scientists who are excited about a new insight, that gets overhyped. I remember when they started arguing we should sequence the human genome because we're going to solve all genetic diseases. Well, yeah, it's that when you get into the details, we sequence the human genome, and some genetic diseases, the very simplest ones, we have cures for. But it's going to take years for those ideas to pan out. But at the time, it got overhyped. There are other examples which might be signals of things getting overhyped. Quantum information became the really cool thing, but the building of an actual quantum computer that can do the actual calculations, like to crack codes and to factorize prime numbers or factorize products of large primes, not there yet. And possibly, although, the jury will be out, the artificial intelligence thing is, I think, in danger of being overhyped. There was also, if you go further back, there was cold fusion. There's all sorts of crazy things that get hyped. And so,
well, even warm fusion, right?
Yeah, warm fusion, indeed. Yeah, warm fusion that's a great one. In fact, that was the latest one. They had this announcement saying we finally got done a fusion process where we got more energy out than we put in. But in that calculation, all they did was they looked at the energy they put into the lasers to fire the pellets. The pellets fused and then they shut down. They didn't factor in the energy to maintain the magnetic fields that's holding in place, or the energy involved in making the pellets. So that experiment was a net negative, and a huge net negative in energy. But they managed to find a way to hype it to say we got more energy out. That struck me as almost irresponsible, that one. But if you've got a huge enterprise and you're excited about it, there's a tendency to hype it. And it's significantly more prevalent in the United States. There are fads, there are things, and this business about, now there's this new fad, we have to hire string theorists, now we have to hire a quantum information person. LIGO created a drive. When LIGO saw these amazing mergers of black holes, astrophysics searchers moved to say, we got to get a LIGO person. You got to jump on the bandwagon where the intellectual activity is. Also, you got to jump on the bandwagon where the government's funding this thing extensively. So, yeah, fads are a thing, and they can be problematic. But the cool thing is that once the fad passes, science does actually work quite well, and the whole system equilibrates. So that once it's no longer fad driven, you should look and see whether the science is still there. Cold fusion has gone away. There were so many fundamental problems with it. But, hot fusion is still an important thing. String theory is still there. All these things that were fads, the healthy thing that happens is that the forces of the scientific community, sociological funding and everything else, equilibrate it and evaluate whether this is still a worthy intellectual enterprise worth studying or funding. And, it's the long-term judgment that matters.
Yeah, I mean, a couple of examples spring to mind. Like when I was a kid, everyone was super excited about room temperature superconductivity because there were big improvements in the temperatures that you could do superconductivity. And everyone thought, oh, we'll have room temperature superconductivity very, very soon. But it didn't pan out. Another one, of course, is hypersonic aeroplanes, because in 1903, we had the very first airplane flight. By 1947, we had the first supersonic airplane flight. And surely hypersonic flight's around the corner. Now, it didn't happen. I mean, it's 2025 now. We still don't have hypersonic airplanes. We're not going on a flight from London to Sydney in 90 minutes. It didn't happen. I don't think I want to say like aviation lied to us, or, material science lied to us, or even the dark matter search. I mean, I believe Angela works in dark matter, and people have made hyped up claims about we're going to find, particle dark matter in mines or on the International Space Station or
Hadronic collider. Yeah. I mean, yeah.
Right. Yeah. And they haven't found out. Do I want to say dark matter lied to us? I mean, it's unfortunate that people overhype stuff, and that it should be guarded against. All right, so let's move on. Let's go to the next clip.
The Wikipedia page for the history of string theory, it does in fact stop in 2003.
Does that mean string theory progress has stopped?
Right. You could argue that the history of humankind stopped 28,000 years ago when Homo sapiens, or whatever, 28 million, whatever it was, Homo sapiens sort of finally beat out the Neanderthals. I mean, if you look at it from an anthropological point of view, then maybe you would argue that, human history stopped when they became the dominant ape species. But if you look at it in the perspective of, human history, there's lots and lots of really exciting and engaging details in there. And the same is true with string theory. If you look at it on a sort of meta-sociological level, then the activity in string theory is starting to drop in 2000s, but it's now reached a stable equilibrium with a lot of really serious and exciting work being done. And we're trying to figure out how to test it, how it changes the way we think about the universe. It's just reached a more stable equilibrium.
All right, let's go to the next clip.
The real physicists, the string theorists, are so brilliant, and it's like Einstein, and no one will listen to them. Oh my gosh. The physicists ignore the truth. The string theorists are going to produce something amazing in the next decade, and then they'll all see, I hate physicists, but I sure do love string theory. And they watch their books. No, they watch their documentaries on Nova by the string theorists about the multiverse. And they read their books, and they're like, real physicists are a problem.
I thought I'd dig up the actual documentary that she's talking about, well, I presume she's talking about, which was the Elegant Universe documentary that Nova made, and to see, what kind of claims were being made in that show. So let's have a quick look.
But this seductive new theory is also controversial. Strings, if they exist, are so small, there's little hope of ever seeing one.
String theory and string theorists do have a real problem. How do you actually test string theory? If you can't test it in the way that we test normal theories, it's not science, it's philosophy. And that's a real problem.
If string theory fails to provide a testable prediction, then nobody should believe it. On the other hand, there's a kind of elegance to these things. And given the history of how theoretical physics has evolved thus far, it is totally conceivable that some, if not all, of these ideas will turn out to be correct.
I think 100 years from now, this particular period when most of the brightest young theoretical physicists worked on string theory will be remembered as a heroic age when theorists tried and succeeded to develop a unified theory of all the phenomena of nature. On the other hand, it may be remembered as a tragic failure. My guess is that it'll be something like the former rather than the latter. But ask me 100 years from now, then I can tell you.
So it seems to me then the claims were not what she said. They're much more measured than that. And they did put the required caveats that this could all be wrong in there. It just isn't the case that they were like, we're the smart ones. All these other doubters are stupid. You'll see. It just doesn't seem to me that's what they said.
And the thing I liked was Jim Gates. You see, he's making this measured statement, but then he gets this smile on his face and say, "But it's and you see the honest answer of the facts, and then you see the natural human enthusiasm that's driving his passion in this subject. That's how it works for all of us. So the measured, careful answers that you showed are what we try to do most of the time, but there's a certain level of human excitement. But again, Jim does not step beyond the bounds of reasonableness in what he says while he's suddenly excited about what he's talking about.
And I should add, to be fair, I'm sure, there were some people that did make really hyperbolic claims.
Right.
I mean, I do find Michio Kaku quite unreasonable,
yes.
quite frankly.
Yes.
So it's not like there is no one making that claim, but the title of a video is that string theory lied to us. And obviously, I don't know how a theory lies, but I presume what she means is string theorists in general, like that, like she's collecting everyone together and putting that on them. And that's what I kind of find objectionable, because the specific cases don't check out.
Indeed. But so let me actually argue against my field a little bit. There is this issue of when you hear someone like Michio Kaku say something outrageous, or maybe one of your colleagues is trying to overhype something. If you remain silent, then that might be a tacit acceptance of that statement. And so perhaps if there's any fault that could be laid at our door, it's that perhaps we did remain silent when some people were overhyping. But then again, what does remaining silent look like? I don't have reporters beating a path to my door every day to ask me what I heard. That. So remaining silent is one thing, but actually having the megaphone is another. And basically, the majority of string theorists do not have the luxury of the megaphone to say, hey, this guy overstates a bit. And, you're absolutely right about Michio. I mean, he's a charming guy, but sometimes he goes way the hell out on an axis.
Yeah, and I do think, if you wanted to pinpoint someone that, makes some really hyperbolic claims that don't seem justified, that would be who I would pick. I wouldn't pick Brian Greene. I think Brian Greene seems quite sensible.
Brian is,
but I don't think you can lump them all together. I think is
and in fact, that's completely unjust. And as I say, in normal society, if you hear something that's wrong, then there is an obligation to speak. But this is not normal society. We're talking about a very, very few people who have a megaphone, public media presence. And most of them, as you've just shown, have been very, very good. And Brian certainly, and the clips you showed, again, the same thing. This sort of measured balance of, here's the reality of whether this is science versus here, if the world, if the universe is the right, configured this way, it's very exciting. And was thinking about it, but we can't prove it.
Okay, let's crack on. Next clip.
The string theorists will prove them. You'll all see. And this, I think, upsets the physicists, the other physicists, the not string theory physicists. They're just like, I'm working so hard. Like, imagine you are a Swiss gentleman and you discover the first planet around an M-class star and you win the Nobel Prize in the 2000s and you're like, yay, exoplanets, hooray, people finally care about exoplanets. I won the Nobel Prize, yay. And then you go to give your interview with the reporter, and the reporter's like, yeah, exoplanet's very cool. How do you feel about string theory? And you have to be like, how do I feel about what? Like, I haven't even heard a talk about string theory in a decade. So books and stuff come out by other physicists who are like, string theory doesn't make any sense. You've been had. Stop listening to string theory. There's this thing, there's this quote from Wolfgang Pauli, who is a very famous physicist. He won the Nobel Prize. Ooh, do I even know? I don't even know what he won. It's something in quantum mechanics, spin or something. I'll look it up and put it on top. Ooh, am I going to edit this? I don't know if I will. Haha, you'll never know what Wolfgang Pauli won the Nobel Prize for. Wolfgang Pauli was like a character. And he is famous for like this story where someone presents him with a physics theory that is very poorly written and like kind of hard to understand. And he replies with, it's not even wrong, like as an insult. Like the theory is so nonsensical that you can't even begin to disprove it. It is an insult because it's like you didn't even take the time to write a good theory. I don't even have the time to explain why it's wrong. It's not even wrong. It's not even a theory. And people start taking this, quote, and applying it to string theory. Because, is it a theory? Remember the three things? I said you have to have a mathematical explanation for the universe, like physical laws, which string theory has. But you also have to explain all past observations, which string theory can do, because they do have the answers. Remember I said that the results of your math can pop up in different dimensions, but if you know what answer you're looking for, because you've already done the experiment, you can get that answer out of string theory. The part where string theory fails is that it doesn't make any suggestions for experiment. It doesn't have any experimental verification. It doesn't have like the way the standard model predicts particles. String theory has not made predictions like that. And if they have made predictions, they're not testable, which means they're not really predictions. So is string theory a theory? I mean, no, it's not. It's like a conjecture. It's like an idea for a theory. It's a mathematical tool, basically. And yeah, that's where we're at in the 2000s. It's kind of like the physicists are annoyed. They're annoyed that this keeps coming up. They're annoyed that their field is misrepresented in the media.
One thing is, I kind of felt like citation needed about the exoplanet scientists, because I tried to look for as many interviews as I could with the relevant scientists. And I went through many of them. I couldn't find a single one where they were asked about string theory. So citation needed, it seems to me.
That's
but what about this issue of it's not even wrong?
One of my peeves, and I think Angela's reflecting that, is well, Angela's peeves also, is bad journalism, lazy journalism. So I could easily imagine that you got this really cool thing that happened, the discovery of exoplanets, and some lazy journalist asked some stupid question. This I'm sure could happen. And so, one of my pet peeves is in fact, every time somebody's going to write some story about asteroids, they go to the Near Earth Orbit catalog and they look at something that's going to hit us or come within 1 million miles of Earth and write a piece about it. That's incredibly lazy journalism. So I think Angela's correctly pointing to one of the damage that lazy journalism can do, and good journalism really is to be treasured. And she cited a really good example of really bad journalism. Anyway, getting on beyond that. So not even wrong. Again, I think we kind of covered this. It's really about the falsifiability of string theory. So if string theory makes predictions, it can be tested in principle. So the complaint is that in practice, in the near future, probably extremely hard. So the people who say, well, it's not even wrong, well, it isn't wrong and it's not even right because in the near future, we probably can't test it. That doesn't mean we shouldn't think about how we might test it. And so, with a suitably creative set of observations and experiments, maybe you can test it, but I have no idea what that was. And if I had even an idea, I'd be working on it. But except black holes. So not even wrong. I think that's completely unjust. Now, there's another argument to be made, which I think is related to what Jim Gates was saying and what Brian has said, is if you take this framework string theory without the experiment, does it give you deeper understanding of things? Does it give you a deeper understanding of field theory? Does it give you a deeper understanding of scattering in a particle accelerator? Does it give you a deeper understanding of black holes or the Big Bang? The answer is yes. It doesn't make a prediction, but it takes the stuff we already know and gives you a much more profound understanding of that thing and can lead to theoretical advances. They're not experimental predictions, and as everybody says, the money shot is to make the experimental prediction and test it. But in the absence of that, you have to adopt a standard, which is this enterprise teaching you stuff that you didn't know and giving you a deeper understanding of real things? And I think the answer is string theory does that.
I wonder if there's an irony about Pauli, because tell me if I've got this wrong, didn't he predict the neutrino and say, I've done a terrible crime because I've made a particle that can never ever be detected?
I don't know that. That's a wonderful piece of history. It's true. That is not a piece of history I know, but scientists make these kinds of predictions all the time. I mean, and are wrong. I mean, Rutherford famously said that nuclear energy is a very poor kind of thing, and anybody who's talking about using it for power generation is talking moonshine. Scientists make predictions and that are perhaps outside their scope, and theorists talking about technology is pretty infamous.
Right. And one thing I want to say about the two books that she referenced, I've read both books, and I don't think they were really saying the same thing. They get lumped together because they were both sort of critical of string theory around roughly the same time. But I think Peter Voigt was probably saying stuff much more in line with what Angela was saying. But Lee Smolin, I don't think was really saying that. From my recollection, it was been a while since I read it. But what he was complaining, not that string theory was definitely a dead end and it was all false and been scammed and things like that, but rather he was complaining about its dominance and that we should be funding, alternative ideas, loop quantum gravity, causal set theory, other approaches to quantum gravity. I don't think he was saying the same thing as what Peter Voigt was saying, but yet they get lumped together as if they were. But I don't think they were. But let's move on to the same.
Yeah, sure.
Okay, let's go to the next clip.
We can move to the 2010s. And wouldn't you know it, the string theorists are like, we're a decade away from something amazing. You guys just wait. Now you have to realize, like, the number of string theorists has dwindled. The universities, I cannot imagine them ever hiring another string theorist.
Okay, so I want to do a bit of fact checking. I looked to see if there were any jobs for string theorists, and my first search found 41 string theory jobs. Now, maybe not all of them are in string theory. Maybe that search has not come out perfectly well. But I did debate a Christian. I do some like atheist Christian debates. I'm the atheist, and I debated a Christian physicist, and he was hired as a string theorist quite recently. So it doesn't seem. It seems like an argument from personal incredulity. Like, I can't imagine a university hiring a string theorist. Doesn't mean universities aren't hiring string theorists. But are they being hired? I mean, maybe you can sort of tell us.
They are, but they're not a high priority in the job. So, for example, at USC, we're hiring in a string theory adjacent area just recently. And it's sort of to reflect the modern new equilibrium that these sort of string theorists have moved into. The people who used to do string theory are now doing things, adjacent, like conformal field theory and things like that, which have impact on string theory. So the hiring is nowhere near as imperative as it used to be, but we're still hiring in high energy physics in string theory adjacent areas quite actively. And
yeah, I mean, I went to some conferences and string theorists were there.
Yeah.
I went to a black hole conference recently, and there were string theorists there were loop theorists there.
Yep.
There were people working in asymptotically safe gravity, all kinds of ideas, and they were all like being discussed on panels.
Yep.
Didn't seem like it's dead.
No, it's not dead at all. As I say, if you've got something that's hugely hyped, when it reaches the sort of stable equilibrium, it might look rather small compared to what it was, and that's what happened. String theory is now, I think, in healthy equilibrium with other fields. It's a really interesting enterprise. There are still people being hired, not at the intensity they were in the 80s and 90s, but, the equilibrium is there.
Okay, let's go to the next section.
They hear the professional physicists, like, not liking string theory, and their response is like, wait, you guys don't like string theory? Wait, you guys kind of, like, laugh at string theory? But I've been following it for 30 years. I've been waiting for the next big thing for 30 years. I've been telling my family about string theory results, and you guys don't even like it. It's not even a real physics theory. And they turn on all physicists. They say, string theorists are liars. They've been saying wait 10 years for 30 years. And I think all physicists are liars. How dare they? And remember, the 2010s is when, I don't know if you guys remember, it's like for like the 10 years, they're trying to get these huge particle accelerators built. Like there was one in Texas, and the particle physicists were like, could we please have $200 billion to build a particle accelerator in Texas? And the public who's interested in physics is like, don't give those physicists any money to test their strings. They're liars. And the public doesn't understand that particle physics is not string theory. Particle physics uses the Standard Model, a very, very successful field of physics, to justify their experiments. Particle physics, linear accelerators, don't have anything to do with string theory, but the public has this connection in their head to physics is string theory because the physicists know, because the string theorists have been going on TV for 30 years and writing their books for 30 years and saying the future of physics is string theory, and I haven't been paying attention. I have no idea where to go. And they lied to the public for 30 years, and now when the public has to hear about other physics, they feel angry. They feel lied to because they were lied to. And even though the particle physicists had their very successful theory and they wanted to build an experiment that, by the way, would work because they did find the Higgs boson in 2012, the public is like, don't give them any more money. We've been giving string theorists billions of dollars for decades and they've done nothing. And the funding for the string theory was never very big. But you hear me. You hear what I'm saying. They're upset. They're upset and they associate all physicists with liars because they were lied to, not by all physicists, but they were lied to for a very long time.
So what's wrong with this claim about the superconducting super collider? Was it cancelled in 1993 because of public disillusionment of string theory in 2010?
So there we go. The time warp problem. There's a lot to contest in there. I was quickly just making mental notes and then forgetting them. Okay. First of all, she makes some comment about there are no results in string theory, which is just completely wrong. But let's get to the meat of this point. The superconducting supercollider was cancelled in 1993, and I remember when the death blow was dealt. It was by Congress. The Mississippi had flooded. They needed $10 billion to fix the flooding, and there was a big $10 billion appropriation that was just shut down. That was the SSC, and the money went over to that. So 1993 is when the death blow was given. Clinton spent a year or two trying to resuscitate it, but by 1994 it was dead. They dug the hole, and there was jokes about turning it into a mushroom farm and things like this. But the chronology here is ridiculous. So in 1993-94, strings was having its second revolution. It was a really exciting period, and so forth. But she's saying, well, in 2010, I'm just saying in 2010, string theorists have been lying, and the public hates us, therefore the superconducting supercollider was killed. No, chronologically, it's completely wrong. I have to say, I made this comment at the beginning of the piece about Angela's becoming part of the problem. This is where she really does become part of the problem. If you're going to make extraordinary claims, you need extraordinary evidence. And she's calling an awful lot of people, Brian Greene and string theorists, liars. And yet she's bringing to the table, as you pointed out, no sociological data. But here she is saying several things that are demonstrably false. And she herself at the beginning of the piece says, scientists have a responsibility to report honestly on things. So, and at that time I said, well, yeah, and the part of the problem is that everybody's sort of got their own social media universes and they're living in this bubble. This particular piece, this section of her video just simply doesn't stand up to scrutiny. There are demonstrably wrong statements. And the damaging one is she's making this thesis that by lying, we've poisoned the well, and therefore the public is not giving money, and that's why the SSC was killed a decade or more before. This is simply not true. It's just that the SSC died for a bunch of reasons, but this was not one of them.
So it wasn't time-traveling physicists going back in time?
No, you're being unfair. I mean, no, it was not. But what's again, when I say just becoming part of the problem, is part of the problem is lazy journalism, poorly researched journalism, not fact-based journalism. And in this particular segment, what she advances as information is actually just simply demonstrably false. And therefore, she is becoming part of the problem of generating fake news or alternative facts in her own sphere. And this is really problematic here.
In fact, it seems somewhat ironic to me because it seems like she's guilty of the very things she's accusing others of doing. And I don't want to say lying because I think stating things that are not true are not evidence-based.
Right.
So, where's the evidence that everyone hates physicists now after they've realized they've been scammed? Where's the evidence? It just...
Okay, so let me step back and just take a little perspective on it. So we both slammed her on this evidence-based stuff. Look, I also viscerally understand that it can be frustrating to see a fad-driven field that maybe as a kid influenced you. So I'm going to get into physics because this is the cool thing I really want to know. And then get there and discover that maybe the field isn't quite what you thought it was or whatever. And you feel kind of disappointed by it. So I understand the human reaction here. But if you're going to go out on a limb and call a whole lot of people liars, you really have to be more responsible in terms of the facts and evidence you advance.
Right. And, I think there's a worry that if people watch videos by physicists who say physicists are liars, might be damaging. I mean, I don't want to say I've got evidence that it is.
That's why I'm saying this is becoming part of the problem.
Yeah. If you think that's a worry, then this is a worry.
Yes, exactly. And she's right about the problem. And in particular, lazy journalism and inept journalism, or just using interviewing based on precepts that are demonstrably false. This is all bad journalism. And
actually, it's a really great example of this that I'm familiar with because I give talks about Aurora Borealis chasing because that's something that I do. And all the time, like every week, we get a headline, or I get a headline on my Google News feed that there's a dangerous solar storm coming to the Earth.
Yes,
it could interrupt the power grid and communications. And it's absolutely false. Every single one of these,
right.
And it doesn't mean that, Aurora chasers or space weather physicists are liars. It just means, people want to sell news stories and they hype things up because they want to get seen by the public because it's hard to get seen by the public.
Right.
And I imagine, maybe one of the motivations for putting out a title for a video, String Theory Lied to Us, is the same. You want to get seen. You want to get all those subscribers, it's exactly the same.
It is. And so, if your income, particularly if your income is based on the number of views, the number of clicks you've got, then there is also the additional financial incentive to be, I'm not saying it's true with Angela, but I think it's probably true with Sabina Hossenfelder, where you want to be more sensationalist than is appropriate. So fortunately, you have the luxury of trying to pull back and say, look, here's where things really lie. But if there's an economic incentive to be sensational, then it just is destructive to a more balanced view of what's going on.
Let's move on to the next clip.
Mm-hmm.
And the public is like, I am done with string theory. And I actually have evidence for this because the TV show The Big Bang Theory came out in 2007. And in 2007, from my little decade by decade, I said the public was like, haha, all physicists hate the string theorists, the true physicists. And that show comes out and the main character is a string theorist, right? And that's his attitude. He's like, I'm better than all the physicists because I'm a string theorist. And the audience is supposed to watch that and be like, haha, I get it. That's my opinion too. But by the end of the show, which happens a decade later, string theory in the public eyes is now a joke. And in the public's eyes, physicists are stupid liars. And that's how they portray the character because the public opinion of string theory shifted.
It is true that Sheldon gave up string theory in The Big Bang Theory.
Right.
Is that not actually, showing a change in the zeitgeist? Weren't they accurately portraying how the public were perceiving string theory?
Wow, you're asking me about the public zeitgeist in America. So I've only seen a few episodes of Big Bang Theory.
What? You don't watch it regularly?
No. I mean, I watched a few of them, but it's one has to pick one's poison when it comes to media. But this is, I saw them film the episode with Stephen Hawking, so that was a lot of fun. So but more seriously, it may have picked up a bit on the zeitgeist, or may have picked up on, there's a physicist who actually came up with is a major player in the Big Bang Theory, who's at UCLA, and it may more reflect, his particular views. But it's always interesting to have your protagonist do something completely radically different. But whether or not something reflects the zeitgeist, I was desperately trying to remember. There's a restoration play written in early 18th century, which has a major character, Dr. Fossil, in it. And Dr. Fossil is this kind of gaga, idiotic guy, but but it's a direct lampoon of Newton. And so Newton was sent up for all his crazy ideas, and it's very common in plays or whatever to send up or ridicule, pretty serious figures. And Newton was ridiculed in the early 18th century. So I find Sheldon, and Big Bang Theory a very engaging show. I didn't watch much of it, but it's neither here nor there. It's capturing what is in the mind of the playwright, which may in fact then reflect some of the zeitgeist. And I'm not going to dispute that string theory has contracted. It's contracted to, I think, a stable and healthy equilibrium. But maybe since it's no longer the biggest fad in the universe, they're no longer in the universe of theorists, that's a healthy thing.
Let me pin you down on something.
Sure.
I want to challenge you. You said there's been progress. Give me the best example of progress in string theory in the last 20 years. Or let's say 25 years. Or something like that.
I would say the black hole information problem. This is a very personal thing. There are probably other things that other people would point to. But for me, it's the insight we've gained into the black hole information problem, starting with the work of Sen, Strom, and Dremwaffe in 1994 through 96. Then the joke I used to say, I have literally given some of the first talks on the black hole information problem, not because I was working on the problem, it's because I was translating Stephen Hawking when he was stating the black hole information problem and what it was. So I have a long history with this subject, and I've always been interested. I only started working on it after Strom and Dremwaffe's work. But the joke I used to say is whenever you went to a seminar that was talking about the information problem starting in 1980 through to about 1995, everybody say, I'm going to throw this new thing. So the first 10 slides, the first few blackboards, whatever, would be something new and different. But then the last 10 slides, the last 10 blackboards would be exactly the same thing. I can't solve the problem. Here's the brick wall I ran into. It's the same brick wall we've been running into for 15 years. That changed in 1995, and it was a direct result of string theory. Suddenly, the information inside a black hole, there was a way in string theory of encoding it. Recycling it's another matter we have to come back to, and now we've been working on how that information looks like inside a black hole. It's been a huge advance. And the cool thing about this is there's a lot of people who are now planning future observations in LIGO and LISA and the Event Horizon Telescope. And they're asking questions like, well, could there be structure at the horizon? Could there be something that Einstein's general relativity theory does not describe or is inconsistent with it? And so in the meetings that we've been organizing, we have 1 or 2 days that are dedicated to trying to talk between the string theorists or the abstract theorists and the people who are actually going to be making the detection mechanisms for the next generation of gravitational wave observatories. I'm not saying it isn't the Tower of Babel, but it's still a very important idea that from the observational side, there are questions like, is the structure at the event horizon? And are the theories that perhaps might say there is structure? This is a very important enterprise. It has a history in particle physics. There's a huge field called beyond the standard model particle physics. And this is where theorists just speculate about what you might discover that is beyond the standard model. And we all know that 98% of it's going to be garbage, but there's the 2% that's really you're shooting for. And the question is, who's got the 2%? It's going to be the same with black holes and structure at the horizon. And I think string theory has a lot to say about that. So for me, that's the most exciting thing. I'm trying to think about other things. I mean, the landscape is a really interesting framework. I mean, so Dremwaffe and was sort of, I think, one of the pioneers of this, asked the question, if you believe there's a quantum theory of gravity and it has to be consistent, what might it tell us about the possibilities for low energy physics? And this is the landscape and the swampland, as it's sometimes called. And originally I was kind of skeptical. Can you tell anything? But the productivity of this set of ideas has been startling. And there are all sorts of really cool new ideas about low energy physics that have come from this examination of what is called the swampland. I have colleagues, one very close colleague who hates the swampland. You can be, it's controversial. But as I say, the one I could stand and hill I can die on happily is black hole physics. I think that's where we're going to learn. We're learning a lot from string theory.
All right, let's move on. I think we're almost at the end now.
In this interview where Brian Greene's like, I never said I believed in string theory. It was in 2021. And he was like, watch out, in the next couple of years, something's going to happen. So maybe I'm wrong. We're going to see. Let's just wait. Let's just sit on it for a decade and we'll see who was right.
That's pretty fast time scale. Look, let's take an example of a new paradigm that's being advanced. In turn of the millennium, 2000, Samir Mathur put forward this fuzzball proposal. And it's part of what I work on. It's a significant part of what I work on. 25 years on. And while the theory of fuzzballs and microstate geometries has hugely developed, there's not a lot of, my colleagues are still deeply skeptical. And rightly so. I mean, this is, again, how science is done. So timescales of revolutionizing things are a lot longer than 1 or 2 years. Now, let me add into the mix. There are two timescales, really. There's the timescale of, here's how long does it take for a radical new idea to be thrown into the mix? That could be a year to 5 years. And so radical new ideas. And then what happens is that probably 2 years later, the bad ones or the ones that don't work die. And you can see that in the tails of citations of papers. And ones and twosies stick around. And perhaps the one with the greatest staying power of a radical new idea is holographic field theory, the ADS-CFT correspondence. This came out of string theory. It's a manifestation of open and closed string duality. And 30 years on, it's 1997, Maldacena proposed this idea. 30 years on, it's one of the most vibrant areas of theoretical particle physics, all forms of holographic field theory. So that's one that's got huge staying power. And our deference, while people might be upset with me putting it in the same box, fuzzballs is still alive 25 years on. It didn't die. It's developed. And so the timescale for throwing out crazy new ideas is 1 to 5 years, probably. And that's probably what Brian is getting at with his 1 to 2 years. But the timescale that you say, okay, is this going to cause the paradigm shift in thinking? Is it going to become part of the infrastructure of theoretical physics? That's measured in decades or hundreds of years. And so I think Brian is exaggerating when he says, well, it might look very primitive. If you're the practitioner of the new crazy idea, then yes, the previous thing will look primitive 2 years on. But from the perspective of other theoretical physicists, it's going to take a long time before something really becomes part of the infrastructure.
Yeah, it did like this quote, it does look like some sort of exaggeration. Yeah. So I think that's a point for Angela.
Yeah,
but on the opposite side, he did make caveats in the past that we shouldn't believe it until it should be tested. And he explicitly said that. And I feel that's the big point, or maybe quite a few points against that.
For 30 years, they're like, the next big thing. It's going to be string theory. It's the next big thing. Just wait a decade. Wait. Oh my God, it's going to be the next big thing. In this book, Brian Greene is like, string theory did in fact combine quantum mechanics and gravity. And it's like, baby girl, that is a lie. That is not true. Maybe mathematically in your conjecture, that thing could work. But did we observe that? Did it happen in 2005? Did you think that was the truth? No, you didn't. That is a lie. You can't write books for 30 years being like, just wait a decade. Oh my gosh, just wait a decade. Things are going to happen. It is a lie. It is a lie to give an interview where you're like, see, the problem with the standard model is that this happens and my theory fixes it. When your theory is not a theory and you don't have any experiments, it is okay to give an interview and say, here's what I'm working on. Here's what I think would happen when we test it. But you need to say when we test it.
Maybe we can summarize where we're at.
Do you want me to summarize?
Well, I mean, I'll give you my closing thoughts. I mean, one, she's basically saying you need to make these caveats when we test it.
Right.
And we've shown, I think, explicitly that Brian Greene, who's the person that she's quoting, did make those caveats.
Although we don't know whether it's right or wrong, and we won't until we have experimental evidence. That really is the arbiter, but has had such progress and made such strides that it needs to be taken very seriously.
Right.
So basically the thesis is they didn't make the caveats when they were made. Then that the public are all hating on physicists now. No data to support that. In fact, the data that we've plugged out seems to show the opposite is true. Well, it's probably stable over time. There's certainly no evidence for what she's saying. And overall, the big picture is that basically, physics, I think, this is my own opinion, needs to come up with speculative ideas. We need to get people excited about them, but we do need to make the caveats that they're not facts until they've been experimentally tested. And there are people that get overexcited. That's true. But the specific cases that she names just aren't applicable, that the caveats were made. So the claims of lying are, well, I wouldn't want to say a lie, but they're certainly false.
Yeah. So stepping back, I look at the concerns that Andrew is expressing, that there's some misrepresentation done by physicists. So those physicists who stand in front of the press are a very, very small section of the community who have a skill at that and who get repeat interviews with the press. And on the whole, they are fairly honest, decent, and they make a decent, on the whole. And on the whole, they're honest and careful. Brian is an exemplar of this. They put all the caveats in. Now, if in a closed room where I'm talking with my colleagues, where I don't need to remind my colleagues that we've got to experimentally test this thing. I don't need to remind my colleagues that, yes, supersymmetry is part of string theory. I start from where my colleagues stand, which is we believe in this structure that we're investigating. We know that it could collapse. We know it could be false, but we're still going to take this thing and build it. And we're going to, the excitement that we generate doing that. So, but when we're doing the research, when we're writing the papers, we try to be very clear about in the background what we can assume is true. But then we speculate like crazy and get excited about it. But when we come out and somebody from the press or somebody from the public asks me about this thing, I will try to give the more nuanced definition in the context of we've got to do experimental tests. But given that, I would also take issue slightly with something you said, that a theory is a fact until we test it. The string theory has had this remarkable deep insight phenomenon into other areas of physics. So it's spawned huge areas of mathematics. So there's a bit more to string theory not being a fact than the experiment reflects, because string theory has spawned huge areas of mathematics, mirror symmetry, for example. So, okay, but I am sympathetic to Angela's concern, but I think her concern is primarily about the poor way in which journalism can be done. But I don't think, with a few exceptions, I don't think we overclaimed with string theory. Certainly string theorists don't go around lying, and we haven't poisoned the entire scientific community against us. I think there is one of the positives that also come out of this thing is there is a grave concern about fad-driven or hype-driven science. And we've talked about a few examples of this, your example with room temperature superconductivity or cold fusion or hot fusion and so on. These things all get hyped. And one of the hugely valuable things that a YouTuber or somebody with a social media connection can do is to call the people out who are overhyping. And I would love to see a discussion from that of what quantum information said it would do versus what is achieved, and what the actual real future quantum information is. It's stunning if it absolutely works, if we have quantum computers. But there will be a nice sort of, let's say, re-equilibration like string theory has gone through. Where is the role of quantum information now in a physics department, a chemistry department, an engineering department? What should we be doing then? And now we've got the new thing, the late new thing, which is artificial intelligence. This is being hyped like crazy. Now there's some serious there, but as a physicist, let me point out, the physics of it isn't the Nobel Prize in Physics. It's for work done in the early 90s. The intellectual property in this field is 30 years old. What's made the difference is this incredible chip, the NVIDIA chip, And so it's being driven by technology, not by fundamental science. And so I'm really curious to see where this is. There's no doubt AI is going to change our lives in some respect, but I'd love to have a more balanced, nuanced, unhyped discussion of what that is. So beware of the hype is, I think, what you should.
I think we can all agree with that. I think Angela, myself, Nick, we would all agree, beware of hype. So maybe that's some common ground that we can find between all of us.
Absolutely.
So we'll end it there. And if you have your own thoughts, please leave them in the comments, and see you on our next discussion.
Okay, fantastic.